Hello, everybody. We have the pleasure today to have as a speaker Meltem Unel from the University of Paris, Saclay, France. Dr. Meltem has obtained her PhD thesis from the Faculty of Science of the University of Copenhagen in 2021, under the supervision of the founder, Derbus. She develops new techniques in random geometry for the purpose of understanding some non-perturbative aspect of quantum gravity in two and higher dimension. The research topics of Dr. Meltem are around the critical behavior of loop models in causal triangulation, trees with power-like height-dependent weight, and trees with exponential height-dependent weight. The talk of Dr. Meltem today has as title Height-coupled trees. Thank you again, Dr. Meltem, and please you can start.
Thank you. So thank you for the invitation. So I will talk about trees with height-dependent weights, and I will focus on the exponential case. There is also the power-like case, as Rafik already mentioned. Sorry, I will turn off my... sorry, it's just to avoid that my mail starts making noises afterwards. Okay. Yeah. So the idea is very simple, but I will explain step by step. So before I will talk about the metric space of rooted planar trees. So this space is well known to the public, maybe, but we just to make sure that we have the necessary background, we consider the planar rooted trees. So they have a root. I don't know if you see my pointer, but I can try to annotate. So they have a root, and that is marked as x0 here. So we consider this is a technical assumption which is not really important, but we consider the trees whose root valency is always equal to 1. That simplifies just the calculations from our approach, but it's not compulsory. And then they are planar, and they're rooted in the sense that the children at every level, let's say this is level 1, they're ordered from left to right. And they can be embedded in this like this, as you see in the picture in the plane. As you embed them, they inherit the ordering from left to right of the children at every level. So the degree of a vertex, we are going to denote it by sigma of j. This is the valency of a vertex. For example, here this vertex has degree 3. And we will name the sectors around the vertex. So if I take this vertex, it has 3 sectors, which means that if you take the disk around this vertex, it's divided into 3 connected components. So this part is going to be the first sector, this is the second, and this is the third sector. We do this because we want to be able to graft trees into the sectors of these around these vertices. So let's delete this. So then I will denote this is just the notational part. I will denote the space of finite trees as T curly T fin. And we can also add to this space the infinite trees, and then I will denote the set of all planar rooted trees, finite or infinite, as curly T. So if we denote, we say that the ball around the root of radius r is the subgraph that is spanned by the vertices that are up until height r. So if I have a tree, let's say like this, so there are vertices, I don't draw them, but the ball br of t, b, which is not the curly b, around the root of radius r is when I just truncate this tree up until level r, and I take what is underneath. So this part is the BR of T. So once we define this, we can put a metric on this space T,
Sorry, question, Meltem. So the ball contains all the loads with depth R, at maximum R. So
Exactly. Yeah.
And what do you mean by capital N in T5? The union of T capital N. What is capital N?
Capital N, this is the size of the tree, yes. So sorry, I didn't say the set of trees with volume N. Here I count, you can count the edges or you can count the vertices as they differ just by one. We name it Tn. Here I think I consider the edges, the number of edges. So is it clear? Should I go on? Is it okay?
Yes, please. Yes, okay. Thank you.
So I put the metric, which is the natural metric. Actually, if two trees, they agree up until height r and at most up until height r, then I will say that the distance between these two trees is given by 1 over r. Okay. So with this distance, this metric space, T-dist, becomes a separable and complete metric space. And then I can define the balls of radius, let's say 1 over r, around a tree in this space curly T, which is given by, if I take a tree, let's say T0, the ball around this tree of radius 1 over r contains all the trees that agree with this T0 up until height r. If that's okay until here, I will go on.
So all trees that have the same edges up to depth r with T0 with T0 is in the ball of radius 1 over r. It's okay? It's right or not?
T0, it's just a tree that I take from my space. It can be any tree. It doesn't have to have height r. Then let's say I just cut it at level r. And I look at the part that is left from after the truncation. And then any tree that contains this tree, that is up until height r, is in the ball of radius 1 over r around this T0. It means that all the trees that have the same behavior up until height r with T0 are in the ball around T0 of radius 1 over r.
Yes, it's clear. Thank you.
Thank you. So we need some more definitions. So there are two types of vertices that I can consider in these trees that I need actually. Those are the finite type vertices and the infinite type vertices. The finite type vertices are the vertices that have a finite number of descendants. So if I'm a vertex, let's say here in this picture, all the vertices that you see are finite type vertices because they have finite number of descendants. But we can also have in an infinite tree, these are locally finite trees, so necessarily we will have infinite type vertices that there is going to be some infinite path to have an infinite tree. And the vertices that are on this infinite path, let's say they are going to, or if there are multiple infinite paths that are on the infinite paths, they are going to be infinite type vertices, which means it's a vertex that has infinite number of descendants. Then what we can do is we can define a map that we say spine map that I denote here by chi on the second line, that will take a tree, an infinite one, because to have infinite type vertices, I need an infinite tree before also. I take an infinite tree, and this map chi is going to delete all the leaves, let's say recursively. So it's going to delete all the finite type vertices from this tree, and I'm going to be left with an infinite tree that has only infinite type vertices. So every vertex is going to have an infinite number of descendants. So this is again an infinite tree. And this map, it turns out to be a Borel measurable map. We are going to need this map. And if I take now the set of infinite trees, and if I look at the image under this spine map, the map that just deletes all the finite type vertices, what I get is the space that I denote by TS. S stands for spine, because these are going to be the spinal trees, or we can call them equivalently as backbone. Why do we want to call it backbone? It's going to be clear towards the end of the presentation. So the final thing that I want to define is the grafting operation. So if I have a finite tree, let's say T0, I take a vertex. Here I take a vertex that I just name it I. And if there are, here you see there are 3 sectors around this I, because the main tree, there are 3 sectors. If I just consider the black tree, the underlying black tree. So what I can do is now I can graft 3 trees inside the 3 sectors around this vertex I. So you see here the red, the blue, and the brown trees that are grafted. Okay. So this map, actually, if I just take now, let's say I take again the black tree and I graft onto the top vertices of this black tree, not on the bottom, but if I just graft, I will try to annotate. Forget about the colored trees, just look at the black one. If I just graft on the top vertices, let's say I graft trees here, 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 actually this map, this is a homeomorphism onto the ball of radius 1/3 around this tree. Okay, so every tree that is in the ball of radius 1/3, because the black tree has height 1/3, around this black tree, I can obtain it by grafting trees onto the maximal vertices. Actually, this is what I'm trying to say. Are there any questions? I'm going to move on. Okay. So what do we want to do? The idea is quite classical. So whenever we have some kind of discrete set of objects, there are some questions that come into the mind. For example, whether I have trees or triangulations, some questions are similar. So I can try to understand. First of all, I can try to count them. If I want to understand how many are there, if I take the size to be large, let's say, if I take n to be large. And then I can also try to do some probability with these objects. So what I can do is I take, let's say, a sequence of probability measures that I call nu n here on the set of objects of size n. I can take uniform probability measure, let's say, on the set of trees T of size n, and then I can try to understand if the sequence of measures, they converge weakly towards a measure that I call nu here, that is supported on the set of infinite trees necessarily, as n tends to infinity. So this is called weak convergence, and the formal definition is here. If the integral of any continuous bounded function f on T with respect to the measure nu n converges to the integral of f with respect to the limiting measure nu, then we say that nu n converges weakly to the measure nu. So how do we, now I will take some sequence of measures and I will try to study the limit of this sequence of measures. But how do I do it practically in the case of, let's say, these discrete trees? So this space of trees, T, they exhibit some properties that facilitate the study of this sequence of measures. So first of all, any ball in T is both open and closed. These they give some as in the classical literature, they call it pi continuity sets. And then two balls, they're either disjoint or one is contained in the other. It's very simple to see these both of these statements. So, but because these conditions are satisfied, or because of these properties, actually, thanks to these properties, one can just study the convergence of nu n if on the balls, on the set of the balls. So for any ball, let's say, in my space, this should have been a curly B, this is my fault. If I take any ball around any tree of arbitrary radius, then if nu n of B converges to nu of B for any ball, then I will say that nu n converges weakly towards mu. These results, given these properties, they follow from classical properties of the convergence of weak convergence of probability measures. So I just want to, yes.
May I ask a question? You said that any ball in T is both open and closed.
Yes.
It's a funny topology that makes the balls.
Yes, it's actually, it's because it comes from its discrete nature. But yeah.
Oh, okay.
This is the.
Okay, thank you.
So this is induced by the distance you just presented before, right? The norm.
Yeah, yeah.
Which, okay. And why is it 1 over r in the distance, in the definition of your distance? So when the distance is 0, actually you get r is infinity.
But I don't have 0 because all the trees, they have at least one edge. I said that the root always has valency 1. But if you don't want to take that edge, you can also define it to be 1 over r plus 1.
Okay, thank you.
This is just a convention. Yeah. Maybe I should just do it that way too, so that it's clearer. But either you put an edge that always has valency 1, or you define the metric to be 1 over 1 plus r. That's the natural metric on the.
Thank you.
T is countable or countable set or uncountable set?
The set of, it's countable.
T. So how do you define continuity on a countable set?
What do you mean? It's continuity with respect to the topology. So continuity of the map, it's if the preimage of any open set is open, then it's gonna, I'm gonna say.
Are you really sure that it is countable? Because I have the impression that you could create at least 2 to
The set of finite trees are countable.
Yes, exactly.
And the set of finite trees are dense in the whole set of T. The set of finite trees are
yes, but the space, I thought that the question was on the space T.
Yeah, okay, sorry. No, it's my mistake, yes. No, the set of finite trees, it's a countable set. It's a countable dense subset. The whole space is not countable, but the set of finite trees is a countable dense subset of T. And that's why it's also, I mean, whenever I have an open subset, I can always cover it with a countable set of balls. This is why that's why from these properties follow the convergence that reduces to the convergence.
Yes, okay.
of balls. This is what I was trying to say, sorry. Is it clear?
Yes.
Okay, thank you.
Okay. So, okay. The question about the continuity, is it also clear? Because I
Yeah, thank you.
Okay, thank you. Okay, so the one last thing that I wanted to say about this is that this object, this limit is called the local limit. So because there are different types of limits that one can consider, namely the local limits and the scaling limits are the most classical known ones. And why do we call it local limit? Actually, the idea of locality is already evident into this condition that is reduced to the convergence on the balls of this sequence of measures. Because remember that the balls actually give information about the trees that agree with a base tree around its root. So the idea of this, but what this kind of limit actually tells us is that if I sit on the root of the tree and I look around, what I see for arbitrary length, but it's for arbitrary radius, but it's always what I see from the root, because the balls actually, they give information about what happens up until some radius around the root. This is why this is called local limit, because it gives a local information, which means that the information around the root of the tree. So there is no scaling like one doesn't bring what is at infinity by scaling to a finite distance, but one really sits down at root, lets the tree get infinite, and then looks around to see what happens actually around root at arbitrary distance, but still from the point of view of the root, let's say. So there is a very well-known case, of course, if I start with the sequence of measures, let's say, that are uniform. So here, this the modulus or the absolute value of tau n, I mean the cardinality of the set. So if I take now the trees, if I want to put the uniform measure on the set of trees of size n, I just need to count them. And we know how to count them. We know that they are given by Catalan numbers, the number of trees in a set of size n. And when I want to put the uniform measure, I just say that the value of a tree of size n under this measure is given by 1 over the number of trees in this set. So we have the uniform measure. So what we know is that in this case, the sequence of measures nu n, they converge weakly towards a limiting measure that we call uniform infinite planar tree. Actually, this is an instance of a more general limit that is called Keston tree. If I take, for the ones who are interested, who are familiar with the domain, if I take Galton-Watson trees, critical, and I condition them by size or by height, it gives the same result for in the critical case, and we have it's with finite variance, let's say. Then the limiting object is called Keston tree, and if I take the Galton-Watson trees, the critical case with the geometric offspring distribution, actually this is reduced to the uniform case, and so the limit is also a Keston tree, and uniform infinite planar tree is just the instance of this limit when the offspring distribution of the underlying Galton-Watson trees is actually geometric. So the important property, let's say, that of the Keston tree that concerns us today for the uniform infinite planar tree case, for the uniform case, is that these are trees that have a single infinite spine, which means that there is one single path that starts at the root and that has infinite length, and finite trees that are grafted onto this spine on both sides. What you see in red, it represents just an infinite branch, it continues. And whenever I have the spine, I have finite, actually IID, independently and identically distributed Galton-Watson trees that are grafted onto both sides of this spine. So this is the uniform case. We know many things about the uniform case. We know the limit, we can characterize it. Now I want to make a small modification. I want to consider a different sequence of measures. So instead of considering the sequence of uniform probability measures, I will weigh every tree by exponential of minus mu h of t. H of t is the height of my tree t. Mu is a real constant. It can be negative or positive, but I will focus on the positive case. So this is the case that when I penalize actually the trees that grow higher and higher. And of course, I have to renormalize by this renormalization factor to obtain a probability measure. This nu n of mu, this is also a sequence of measures. They are no more, this is no more uniform. It's no more the sequence of uniform measures. And I can ask the same question. I can ask if this sequence of measures admits actually a weak limit in this case. And this is what we will study. Is it okay, the idea? I will go into the construction.
Is there any relation between this distribution and the Ising model or Gibbs model?
This is a Gibbsian measure, if you want.
Okay.
I mean, it's if you want to just say that I want to just study the critical behavior of this, if you want to see it as a statistical mechanical model, yes. But in terms of Ising model, I mean, this kind of distribution, actually, we saw it in the study of this loop models on causal triangulations. Causal triangulations are in bijection with the rooted planar trees. And the loop models are related to the clusters of the Ising model, but the connection is quite long. So it's not a priori direct.
So mu is not a temperature. The significance of mu is not the temperature in.
I mean, if you want to see it's like the inverse temperature, no, I mean, not necessarily. It's a coupling constant. But yeah, I mean, it's possible if you want to interpret it as that, you can call it that, but it has nothing to do with the temperature, of course, a priori.
Okay. Thank you.
So how do we actually study these models? What we want to understand is the generating functions of trees, let's say, that have height m. Because if I can do that, actually, I can say, okay, if I know, for example, the number of trees, if I can count exactly the number of trees that have size n and height n, and size n and height m, then I can just weigh them by exponential minus mu times m, if they have exactly that height, and I can sum over them to obtain the generating functions. So to do that, we first write down the generating functions of the trees that have height up until m, because it's easy to obtain these generating functions recursively. So amn are the number of trees that have size n and height at most m or smaller. Okay. So G is here G is just a complex parameter, and we study the critical behavior of these generating functions to obtain the coefficient asymptotics of amn. This is these are classical, how to say, a classical way to deal with the problem, the analytic combinatorial approach to study the generating functions and the singular behavior of the generating function that gives information about the asymptotics of the coefficients. So we actually know the solution, the exact solution to this problem. We know the explicit form of these generating functions, xm of g as a function of g. These are Chebyshev polynomials of second kind. Their behavior is well known. So at the end, these are functions that have actually that have poles whose corresponding residues we can calculate. Actually, I think they have k over 2 poles. K over 2, you have to take the integer part, and sorry, m over 2. And then these coefficients, amn, they can be calculated from the critical behavior of these functions. So I didn't give any details here because they're just some calculations for the residues. Is it okay up until now?
What is the condition that guarantees that amn in this last expression is an integer value? Because we see it tangent function, and it's not easy to see at the first time that amn is actually an integer value.
Yeah, that's true. Let me think. So if I have,
For example, you take m equal 2 and n equal 1, for example. N equal 1 and n equal 2.
yeah, I mean, it's not clear from the form, but this is an exact solution. So
Okay.
I don't know. I don't know, but I will look at it.
So we can say that as a corollary that this expression, this form, leads to an integer value. Okay.
Yeah, I don't see clearly a simple argument.
And is what is the function um in x
These are
and g?
Chebyshev polynomials of second kind.
Okay.
I go on?
Yes, please.
Okay, so how do I use these coefficients actually? Now I have exact coefficients. I know the form of AMNs. So what I can do is I can use them actually to compute these normalization factors that I needed to get to, that I used to normalize, to get probability measures nu and mu. So actually, we look at what we have to do, we have to look at the nth coefficient of the difference of these partition functions of trees that have at most height m, because if I take the difference xm minus 1, what I obtain is exactly the generating function of trees that have exactly height m, right? And then I have to couple them to exponential minus mu m, because every tree that has height m gets a weight factor that is exponential minus mu m. And then these xm's, remember that they're functions of g. And if I then look at if I expand them as in g and look at the coefficient of the g to the n, I have to get exactly these numbers amn minus m minus 1, am minus 1 n, weighted by these factors exponential minus mu m. And I know the explicit form of these coefficients amn and am minus 1 n, and I can try to now study directly using the explicit expressions of amn and am minus 1 n together with these weight factors to obtain the coefficient asymptotics of Zn of the Zn of mu that you see here. So this is the proposition that gives the coefficient asymptotics. Actually, this result we saw it afterwards with someone told us that it existed without proof in a paper of Gottman, where he analyzes it using dig paths, which are in one-to-one correspondence with the contour functions of the trees. So it existed before, apparently, but I state the proposition because we need it. So they are given the coefficient asymptotics for large n, Zn of mu behaves in this way. This is the asymptotic form, let's say. So the dominant behavior is given, let's just look at the n-dependent terms by this exponential minus a n to the 1/3, and then there are these other factors. But if you look at just the exponential part, because we weighted every tree by this exponential minus mu times h of t, this actually gives us already the clue about the height of the trees that dominate this ensemble. They are the trees actually that have height on the order n to the 1/3. Actually, one can directly use this expression to calculate the expected value of the height of trees in this of the height of trees that have size n, and it comes out to be of the order n to the 1/3. I just want to make annotate, yes. So if I look at remember the case of the of the uniform case, let's say uniform, and if I look at the expected value of the height, it's just a reminder. This is of height, I mean, uniform measure on the set of trees of size n. This turns out to be on the order square root of n. Okay. So this is the generic case. But in our case, if I take nu mu, then I will get, this is not equal, but this is on the order, I think there is a square root of pi as a constant. And here, this is of order n to 1/3. So this already gives the clue about the fact that the local limit is probably not going to be the same as the local limit of uniform infinite planar trees. I'll move on. Are there any questions? Okay, so I will pass the sketch of proof, but if there are questions later on, we can come back. But basically, the idea is to approximate it with a saddle point approximation. This is exactly, it follows from what I tried to explain before. Sorry, I'm a bit, this annotation confuses me. Sorry, it moves on. Yeah. So the idea is to look at the part of the sum where actually the height of the trees are of the order n to the 1/3, and use a saddle point approximation that around the height n to the where the height of the tree is of the order n to the 1/3, and this is how we obtain the coefficient asymptotics. And the reason why we look at this window where the height of the tree is on the order of n to the 1/3 is explicit. Actually, it comes from the idea that the expected value of the height of the trees are of the order h to the n to the 1/3, which means that the ensemble of the subset of trees that dominate this ensemble with the given weight factors are actually trees that have their height on the order n to the 1/3. Is that okay up until now?
Yes, thank you.
Okay. So how can we continue to, how can we now use this result actually of coefficient asymptotics to show that the sequence of measures nu and converge weakly towards a limiting measure nu? We will use a standard theorem that is called the portmanteau theorem from the classical literature. To do that, remember that it was sufficient to show the convergence on the balls. So we will bound the volume of balls under this measure. We will find the lower bound, and then we will use the portmanteau theorem to obtain the final result of the convergence. So this is a rather complicated expression. So, but it's actually not so hard to decode. I will try to just to get your attention to the following point. So if we look at this expression, then what we see is we have a tree of T0 in this lemma that has exactly k vertices at height r, at its maximal height, okay? Remember that I said in this grafting map that any tree that is in the ball of radius 1/r of this tree of height r T0 can be obtained by grafting trees on the top vertices, on the vertices at maximal height of this tree. So if I now graft trees, what kind of trees do I graft? Do I graft infinite trees? Am I going to graft infinite trees, or am I going to graft finite trees to obtain the limiting behavior, the large trees or the small trees. So actually, this expression that you see on the bottom of the page, when we take n to infinity, gives us the answer to this question. The expression tends to this, this expression that you see on the bottom, that tells you that I have to choose r vertices out of these k vertices. And what I will do actually to obtain the trees in the ball around T0 of radius 1 over r is to graft infinite trees on top of these r vertices that I choose, and to graft finite trees on top of the rest of these r vertices. This is of course, it is not obvious in the first regard from this expression, but it gives us a clue that when it tells us, but I have to choose r vertices, it already makes us doubt about the fact that there might be there might be more than one, possibly infinite branches that I will graft on the top vertices of this finite tree. So this actually this is just stated, not this, but the limiting measure, the existence of the limiting measure and the identification of the limiting measure with the limiting measure that is known from another work of Abraham, Delmas and Bouaziz is given in this theorem. So for each positive mu, this sequence of measures nu n converges weakly to a limiting measure nu mu that is supported on the set of infinite trees actually, and the ball volumes are given by the expression that you see on the screen. Actually, because we are talking about the local limit with the properties, remember, with the properties that I had given of the balls and the fact that the convergence is fully characterized by the balls, it's actually also true that the measure is fully characterized by the ball. So if we know the volume of any ball, if we know how to compute the volume of any ball in this space, we actually know everything about the measure. We can characterize actually this limiting measure. So this limiting measure is actually also encountered in another paper by Abraham, Delmas and Bouaziz. And they call this limiting measure the Poisson tree. They construct it in a different way. They take Bienem-Galton-Watson trees. They condition on the size of population at a certain height. They condition, let's say, in vague terms, that the population is large at some given height, is larger than the, let's say, generic case actually. And we can now use just the portmanteau theorem to deduce the fact that this measure is actually given by the Poisson measure, by the Poisson tree that is characterized in their paper. Without using this characterization of this limiting measure that is given already as a result in their paper, it is also possible to prove that the measure exists, and then we don't have to pass from the portmanteau theorem, because to use the portmanteau theorem, we have to know the limiting measure. If we know the limiting measure, the Poisson tree, that we call the Poisson tree, we can use the portmanteau theorem to show that actually from what we calculated, we can deduce using the portmanteau theorem that the limiting measure is the Poisson tree that is given by the results already. But even if we don't have this limiting measure result, if we don't know the explicit form of the limiting measure, it is also possible by using these results, one needs to do a bit more calculation, that the limiting measure exists, and it is characterized by this value, by these volumes on the balls. This is just a side remark for people who are interested in the local limits. I move on, if it is okay. So what do we know so far? We started by this sequence of measures that attributes exponential weights that penalize the trees that are high. And then we derived some coefficient asymptotics, and at the end, we proved that actually this sequence of measures, they converge weakly towards a limiting measure, nu mu, and we know how this measure is characterized. But on the balls, what I mean is that we know the value of the balls, of the volume of the balls under this measure. So using that, actually, is it possible to do a further characterization of this measure? This is what I will try to do. So just a simple definition. I will call the mu scaled simplex, and I denote it by mu delta n, as this n-uplet and this mu1 to mu n, where the sum of this mu1 to mu m is equal to mu, and where every one of them is positive. Okay. So it is just the simplex. Normally the simplex would be when mu is equal to 1, the standard simplex. But here it is the mu scaled one. So the sum of mu1 to mu m is equal to mu and not to 1. And we can simply have the uniform probability measure on this simplex. And what we will denote it by omega, the small omega. So it is possible also to show that actually what you see on the second expression is a probability measure on the product space tau t to the n, which means the copy or n copies of the state of trees. And one more definition or just a background. So I will give the explicit expression of the Bienem-Galton-Watson measure rho on the set of finite trees, because if I have the Bienem-Galton-Watson trees, if I take a offspring distribution and I take the critical case with the geometric distribution, actually this induces the what we call the Bienem-Galton-Watson measure on the set of finite trees, and these trees, a tree T has mass under this measure as 2 times 4 to the minus the volume of the tree, which means the number of edges. So this is the Bienem-Galton-Watson measure rho in the critical case with the geometric offspring distribution, which, remember, that was corresponding once we look at the value of the measure, once we restrict this measure to the set of trees of size n, this becomes the uniform measure. So the following theorem is the decomposition of the measure nu mu once we restrict it on the ball of radius 1 over r around T0, where T0 is a tree of height r. So I will try to annotate maybe. So I take a tree, T0, of height r, and I look at the ball around this tree. Remember that all the trees in this ball can be obtained by just grafting trees onto the maximal vertices, or the vertices at maximal height, let's say. So what I tried to say before, when we saw the value of the balls under this measure, about choosing R vertices among these K vertices, K top vertices, actually becomes explicit here. What does this say to us? It says that, okay, the measure nu mu restricted to the ball is given by, okay, let's forget about the constant factors. T0 is just the volume of this tree that is up until height r. So these are just constants. So let's look at this sum. This sum tells us to choose a subset of these K vertices. There are K vertices at height r, a subset of these k vertices that is non-empty. Okay. And what this integral tells us is that I have to graft now infinite trees on the vertices in this subset. Let's say, for example, let's say that this subset, it has two vertices inside. So on top of these two vertices, I will need to graft infinite trees whose joint law is given by this probability measure here in this integral. This tells us that I will have an infinite tree, mu I, which has mu I as in the exponential weight factor, exponential minus mu I times h times t. And the sum of these mu i's, they have to add up to mu. So if I have a mu1 here, let's say an instance in this integral, I choose mu1 and mu2, just to give the example, just to give the intuition. If I graph the two infinite trees, then they will have, I have to take mu1 and mu2 such that mu1 plus mu2 is equal to mu. And I have to integrate over all such partitions of mu between mu1 and mu2. When I take this D is this subset is just these two vertices now, and then I have to take the sum over all possible subsets that I can choose out of these k vertices at maximal height. Okay. And then for the, what do I do with the rest of the vertices? Here I chose two, let's say k is equal to 5. I chose two of them. I have to graft infinite trees whose joint law is given by this expression, you see. And then what do I do with the rest? On top of the rest, I just graft independent and identical Bienem-Galton-Watson trees whose this rho j is just equal to rho. It is the Bienem-Galton-Watson measure corresponding to the critical geometric case. It's the, as I explained in the previous slide, that is a measure that is supported on a set of finite trees. So I have infinite trees here that whose law, who had this kind of partition, who partitioned this weight factor mu, and I have finite trees that I graphed on top of this. The rest of the vertices after I choose this subset D. Is it okay? So I will move on. Okay. So the last thing that I want to talk about, because I don't have any more time left, is that actually remember that we had what I call the spine map, that I could take an infinite tree, such an infinite tree, and then I delete all the finite type vertices, okay? So if I take, let's say, a Keston tree, an infinite tree with just one infinite path, one spine, with finite trees that are grafted on this spine, and I apply this map chi, the spine map that deletes all the finite type vertices, I just end up with one path that is one infinite path. This is because the Keston trees are the trees that have one infinite path with some finite trees grafted on the vertices of this infinite spine. Here, if I do the same thing, actually, what I can do, I can look at the push forward measure under this map of mu that is defined in the classical way as the push forward measure is defined. That is going to give me the spine trees on which this push forward measure, I mean, I want to get some information about the trees on which this push forward measure is supported. Okay. And we can study it. So if I take, let's say, a tree that can be part of a backbone tree, which by which I'm trying to say that if I take a tree that has leaves only at maximal height and no other leaves, like this one, for example. Okay. And then I look at the ball around it, which means all the trees that have only infinite type vertices in the set of this TS, the set of spinal trees. And I look at the volume of this ball under this push forward measure, I get this expression. Okay. And if I look now at the pre-image of this ball, what I find is this decomposition. I will show a picture which explains this. Okay, this one. Sorry. So I almost finished. I'm trying to delete this. So what does this measure say? This expression say? This expression says that if I take a tree, okay, T0S, that is possibly a part of that is a spinal tree, let's say, that is a tree with only infinite type vertices. Then I look at the ball around this tree in the set of spinal trees, which means the trees that have only infinite type vertices. And then I look at the pre-image of this set of balls conditioned on this event. Actually, my measure is decomposed in this way, which means that all the trees that contain this black tree as part of its backbone have the following form. On top of these vertices, because this black tree has to be part of the backbone. So all the vertices on this black tree, they have to be infinite type vertices, which means that I have to graft infinite branches here. This is the expression that tells me to do this. Okay. So I have R vertices at distance R. Here are little r. Little r is a 3 here in this picture. And I have 3. This is also 3. This is just a coincidence. And I graphed infinite branches here. And they have a joint law that is dictated by this measure here. And what do I do with the rest? With the rest, I graphed again identically and independently distributed Bienem-Galton-Watson trees, which are finite trees that you see in blue. And I have to graft it into every sector around these black vertices. Just to say a final word. Okay. So we can actually compute further quantities using this push forward measure nu tilde. We actually know that if I look at the increments zeta r, that is the number of vertices, that the difference of the number of generations between r plus 1 and r, at the level r plus 1 and r, this is actually a Poisson random variable. And using this together with the information that onto the small sectors around the spinal tree, onto the sectors that are onto the sectors around the vertices that are not at maximal height, I grafted this finite Bienem-Galton-Watson trees. Remember these blue blobs. By using these two, actually we can compute the exponent of the volume growth of the balls around the root, which turn out to be on the order of r to the 3. Okay. So this means that as a function of radius, the expected value of the balls around the root, the size of the balls, the volume of the balls, they grow as r to the 3. In the generic case, this is r squared, and this exponent is also called Hausdorff dimension. So in the case of uniform case, the Hausdorff dimension is equal to 2 actually, but here it is equal to 3. This is what also characterizes the difference of this measure. So I will stop here, and if you have questions, then just to stick to the time, I think it's almost time. Yes.
Thank you, Meltem. Thank you very much for this nice presentation and also for your generosity in answering to questions during all your talk. Are there some questions, please?
So maybe at the end it got a bit more complicated. I should get an iPad to be able to draw.
Please, if you can go to slide 6. Slide 6. Why you ask that the trees are IID Galton Watson
No,
trees?
it becomes like that in the this is the case when I have the geometric critical BNM Galton Watson trees. I don't ask it, but the limit is like that. So
Okay.
if I take BNM Galton Watson trees with the geometric offspring distribution, critical case, with the geometric offspring distribution, actually in the limit, we see IID Galton Watson trees grafted on the spine, but this is specific to the geometric case.
Okay, okay. Another question may be that I have not really understand the model, but the number of the our degree of any node is random or given or deterministic.
Sorry, the output of?
Our degree of any age is random variable or how we can fix our degree, the number of children of any node in this tree, in any tree.
The root, you mean?
Okay, for the root. It
For
is,
the root of...
it is deterministic or
No. I mean, in our case, it is deterministic in the sense that because I consider these type of trees that all the trees they have root of valency 1. But let's forget about this one and let's look at the one that is marked as phi 2I. Yeah, it is random, of course.
It is random. Okay. With some distribution or
it's possible to compute it.
okay.
I did compute it at some point, but I don't have the expression here, but it's in one of my notebooks, yes.
Okay. Slide 8, please. I think that the remark of our colleague Eddie Nabli is very important that why AMN is surely an integer number. It is not clear in the sum.
Maybe Cyril has an opinion. He's an expert on...
Well, I don't have a direct answer to it. I guess that possibly it should be possible to handle the tangent number here and to find it to get a kind of independent proof that at the end you get integer. But you have a lot of kind of tangent, cosine, sine formulas for lattice path enumeration, which were obtained 200 years ago by in the compte rendu de l'Académie des Sciences by people like Rouchet and so on for similar problems which were called the problem de la ruine. So it's the same as asking the probability that some works is going below 0. And for this, they got those expression in terms of sine and cosine. And in fact, it's for models which are related to DigPath. So behind all of this, what you have is stuff which are in fact related to Chebyshev polynomials, for which also those sines, cosine parametrizations are natural ones.
This is how we obtain this expression.
So I would say that the proof that they are integer is because of the combinatorial definition that you gave.
Yeah, that's true. So if the expressions are true, are correct, then it's a proof that actually they have to be integers.
And but if you don't know the combinatorics which is behind, I think that it is indeed some could be some funny Olympiad problem to prove that those identities or that those numbers are integer sequences.
Yeah. I mean, I cannot see it at the first look also. I mean,
Yeah, you have some variants of this also, which can generate all the prime numbers, which
Yeah.
are kind of hidden behind Wilson theorem and properties of sines, cosines, tangent numbers. So it's yeah, sometimes you have stuff which are not trivially integers, but which are at the end are integers. But I have another question. Your trees, they have a left and a right children. So the children are ordered. They are
Yeah.
in the plane. So if you consider unordered trees, so sometimes they could be called Cayley trees, for example, in which you could permute any subtree. Okay. So and if you allow any arity, they are counted by the n to the n minus one. Enfin, this is the Cayley trees. Then it's also families of trees on which you could ask for a notion of backbone. You could cut the finite parts and have a limiting object. Did you consider this model? Do you know some stuff on this model?
No, but you should. Yeah, no, we didn't. No, actually, I never thought about it. It's a good question, but maybe, I mean, I would expect that you get some kind of partitioning in a similar way. But you have to normalize somehow, I suppose, to get rid of the redundancies of you know, when you have permutations of.
Yes, so in fact, yes. So the natural models below Cayley trees is that they are labeled. So the nodes will have integers values. So so that it is kind of immediately it's easy to handle the symmetries of your object. It's just you have all the possible, you divide by the n factorial permutations.
Yeah. So I don't. Yeah.
The other model which will be harder will be polyatries, because then you have to handle the symmetries that you had in mind.
Yeah.
But it could be expected that probably polyatries will behave like your trees, but I'm not sure exactly what it would give. And I am not sure either of what could be the equivalent of this tangent formula that you had for stuff of a given height, and you need to generalize this to any families of trees. And in full generality, there is no such direct formula. But however, what you really need, in fact, it's not this formula. You need the asymptotics of this formula.
Yeah. Yeah, I don't have a priori any intuition about what. But I mean, it should be possible with a similar recursive idea to write down the generating function, no?
It's possible to write some kind of functional equation for these generating functions.
Yes, and then if it can be solved or not, that's a different.
They won't have some nice expression in terms of Chebyshev or whatever in full generality, but some type of similar asymptotics, which should be handled one day.
Yeah.
And I have also another questions. So you have some objects for which there is not a natural notion of left and right, for example, like planar maps, for which possibly it could be, you could have perhaps a notion of some type of backbone or stuff like this, which is not that clear in which way to define. So you need kind of to route your map and then to have a kind of recursive decomposition of it. So do you know if there are some objects beyond trees to which those ideas were applied?
You mean if these trees can be the backbone of some kind of planar maps?
Yes, if you could use the results because of structures which could be kind of in bijection or transformation of your objects, or a similar type of proof.
Yeah, I mean, we know that any planar tree is in bijection with the causal triangulation, so they will be in bijection with causal triangulations. but any kind of other planar map, I don't know, because causal triangulation is okay. Yeah.
Yes, triangulation exactly is the one for which it should work nicely, but we could expect some type of perhaps universality behind all of these models, and therefore, even if you don't have exactly triangulations, it should behave in a similar way. I don't know if it is possible to argue like this, or if it will be really model dependent.
Yeah, I don't know. Actually, I mean, it might be interesting also to try to see for example, the geodesic properties, let's say, of the causal triangulations that can be constructed from this, because then you will start having the horizontal edges.
Mm-hmm.
And for example, as just the random triangulations without the causality conditions, they have Hausdorff dimension 4, and the generic causal triangulations, they have Hausdorff dimension 2, and these will be Hausdorff dimension 3. And I don't know if adding the horizontal edges, constructing the triangulation, how it will affect, for example, the distance between, let's say, two arbitrary points.
Mm-hmm.
I don't know.
And it's funny because for this problem, it's also a little bit related to history, not of probability theory, but of combinatorics, because enumeration of triangulation, in fact, was solved by Euler, for which he found that it was contained by Catalan numbers 1 century before the birth of Catalan. So he had this already a long time ago. So here you go back to two very old problems of the foundation of probability theory and of combinatorics.
Yeah. Like interpolate the problems of combinatorics.
Yeah. Yes, perhaps some model on which those type of limit shape backbone could be applied could be some models of permutations avoiding some patterns. Because behind some of them, sometimes you have some objects which could be quite near from some type of Brownian motions or variant of Brownian motions. So by analogy with random walks, here perhaps it could work on permutation.
I took my notes.
Mm-hmm.
And yeah.
We have possibly even some expert of this in the room. Not sure.
Yeah, I don't.
Other questions, please?
Yes.
Yes, Eddie.
Thank you. So with reference to Ising model, what happens when mu tends to infinity?
What do you mean by the Ising model?
The parameter mu.
But I cannot get the connection with the Ising model.
No, so I think that the idea is that you have your, you said that it was a Gibbs model.
Yeah.
So E mu to the blah, 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 it's like a Gibbs measure. So by analogy with this Gibbs model, people, if you send mu to 0, temperature will go to, mu to
here, mu infinity,
temperature will
because,
go to 0. So this is not exactly the Ising model, but by analogy, when you play with the temperature, with the mu, when you send it to mu to infinity, it's like if you send the temperature to 0 in one sense.
Yeah.
This is right.
Yeah, I see. Actually, it depends. I mean, we have an ongoing work about the different cases when mu, let's say, tends to 0 or to infinity. And we expect to observe some kind of condensation phenomenon when mu tends to infinity, but I mean, it depends on the speed as a function of n. If you let mu to depend on the size,
Okay.
and then you can look at what happens, for example, if mu n is of the order n or higher order. And there is a threshold. I cannot tell you like this from my head at the moment, but there's a threshold where one starts seeing a condensation around which means the infinite degree vertices start to pop up. For mu going to 0, it also depends on the speed of the convergence to zero. One starts expecting different behaviors. There is a window where you see the mu constant behavior, and then there is a window that one can expect to see different limiting objects, but this is a calculation that I'm doing at the moment, so I cannot tell you exactly.
Okay. Besides the mathematical development, are there any applications on mechanical or I don't know?
I don't know. I mean,
the motivation is only mathematical. So
I mean, as I said, actually, it was from a statistical mechanical model that we got the motivation to study this problem. We were working on the loop models on causal triangulations. And there, one of the loop models, to understand the critical behavior, you get a factor of 2 to the height of your causal triangulation. And this is
in
where,
this case, can you give a probabilistic interpretation or a physical interpretation of the limiting distribution?
but okay, in that other case, the difference is that it is like a case where mu is negative, not positive. So in that case, you favorize actually the ones that are higher, or at every level of your triangulation, the way that you can construct the loop is, I mean, if you fix a configuration, then you multiply it by 2, because there are 2 ways of completing the loop. So let's say given a subset of vertices at a certain level. And this gives the other scenario. But for penalizing it, a statistical mechanical model that requires penalization by the height, I don't know. I mean, I didn't encounter it. I haven't encountered it. And it would be interesting to know why and how. Yeah, but there are some, for example, works on the Brownian motion that is penalized by its range. But yeah, these are all mathematical works that I know. But maybe they could be important for diffusion problems in that case. Penalization by the range, because range.
Yes, and in the room we have also some people who played with those model of random walks on which you put some weight on jumps which are done at a given altitude, which bias your walks, and you get stretch exponentials phenomenon. So Michel Wallner and I don't know if other people from there could perhaps give other application of this. In fact, it has some applications outside the direct model.
It will be interesting to take a look.
Yes, Michel told that he had the
application,
microphone. So
sometimes we get some inspiration from applications, even in even mathematical inspiration. Okay, so
yes, so here, because you have also some when you were doing the enumeration for binary trees, so it will be related to dig path plus or minus 1 lattice path or Bernoulli path, or many different possible names for them. And then you could have a kind of continuous fraction representation of them, and it will be related that in your continuous fraction you put some weight which is proportional to the depth in your continued fraction. So it's also a funny way to have some bias like this on in your jumps.
But in terms of physical application, yeah, I don't know. Yeah, maybe some diffusion model.
Yes, any model in which the further away you are from the origin, the higher or the lower the weight of your jumps are, something like this. You can. So this is really the intuition which is behind this model, and you can have it for a lot of stuff. But in the work that some people did recently in analytic combinatorics. It was also leading to some funny enumerations of the objects which are a priori not at all related to lattice path. So yeah. Because in fact it's possible to use then those models to have some type of upper bounds or lower bounds on some other type of recurrences, let's say. And then you go to this lattice path with weights on which you have a little bit, let's say, possibly more intuition in which way to handle them. So it gives some models of upper and lower bounds for some other models that you can then handle.
Okay, thank you for all. If there are other questions, they can be asked via email. The email will be on the first slide of this talk. The slide will be published on the homepage of our webinar tomorrow. Thank you, Dr. Meltem. But before ending this session, I think that our speaker has some announcement. Meltem, you have an announcement to
Yes.
give? Okay.
So we are.
School.
I will just, yes, exactly. So we are organizing a summer school in Turkey, in Mathematics Village in Turkey. I will put the link to the chat. The public that we aim for is the bachelor's and master's students that are interested in probability. So the applications are going to be closed very soon. So if you have students that are possibly interested, I put the link in the chat, and we can cover the accommodation of the students. The travel expenses, not really, because we don't have that much of funding, but we do our best to get more. But the accommodation we can cover. So yeah, if you have students that are interested in these questions, in these topics, you will see the courses. Yeah. And so it is until the end of this month that the applications are open, because afterwards we have to finalize the organization.
So good luck with it.
Ask it to your students if you have students that can be interested into. There are going to be Galton-Watson trees, local limits, random assignment problems.
Rafik, you can go down. You have the list of the courses at the bottom of the page that you are showing.
Yes. Sorry.
Yeah, exactly. Yes.
Okay. Random walks. Okay. This one.
Yes, these are the 4 courses.
Okay. Thank you. Thank you, Meltem. Thank you again for your nice talk and for answering all the questions of our public. Thank you for the public.
I tried. I couldn't answer all, but I tried. Thank you for the questions.
And we see you next week for another talk about mathematics for artificial intelligence next Monday. Not next Tuesday, sorry. Thank you for all.
Okay.
Thank
you
you.
again.
Thank you.
Thank you. Thank you. I stop.
Thank you.
For now.
Good evening.
C'est bon, Rafik, je coupe.
Oh oui, tu coupes. Moi, j'ai coupé, non?
Allez,
Je pense-
salut.
Je pense que j'ai coupé. Hein.
Allez, à la prochaine, salut.
À la
Salut.
prochaine.
À la prochaine.
Vraiment.
Merci, merci, Saïd.
Merci, merci.
Merci pour toi.
Merci.
Merci beaucoup,
Au revoir.
Cyril.